Okay, last class we completed with which topic? So we completed with the dynamic CMOS. No? So today we start about the this technology that is nothing but FinFET technology. Okay. So my screen is visible. No? Just please confirm so that I will move forward. Working and fabrication of FinFET. Hello. Yes. Hello. Anyone? Give response. Shall I move forward? Hello. Yeah. Okay. Thank you. So see here. So basic first we'll see the basic outline of FinFET, structure of FinFET, and double gate tri-state FinFET, and HG FinFET, IG FinFET, top view of FinFET, what is the fabrication of process of FinFET, characteristics of FinFET, advantages of FinFET, disadvantages and application we'll see. Okay. So basically, like so what is this FinFET means? It is a type of multi-gate MOSFET. So in the CMOS, in the MOSFET, okay, in the MOSFET we already seen now. So MOSFET you have single gate only. Okay, you have single gate. Okay, but in FinFET you have multiple multi-gate. Okay, you have multi-gate MOSFET. Okay, so it is widely used over planar CMOSFET. Okay, so this is widely used over planar CMOSFET. Fin is nothing but what channel. Fin is nothing but what channel. So we already seen in the MOSFET. So channel is formed between what between source and drain. So channel is between in the enhancement MOSFET we already seen that channel is not there. So we need to induce the channel by applying gate to source voltage. And the depletion MOSFET we already seen channel is there, and we can operate both in enhancement as well as depletion mode. So fin is nothing but what channel. Okay, channel. So that you know the channel. Channel is nothing but this is the thin layer in this whatever the charge carriers are there that will flow. Okay, so that is nothing but fin is nothing but channel. Okay, so fin can have what FinFET can have two or four or more fins. Okay, so it can have two channels, it can have two channels, or it can have four channels. Okay, two channels and four channels. Okay, on the same structure. Okay, so it can give the advantages over the normal planar FET. So what are the advantages? Area performance, low leakage power, low voltage operation, low retention voltage from SRAM, and it has better control over current. Okay, this is the main advantage of FinFET over normal planar FET. Okay, so like a traditional planar MOSFET will be like this. So that means you have what we call like so drain and source and substrate and there will be oxide. Okay, there will be oxide and there will be gate like this. Okay, this is a basic planar structure, and this is nothing but FinFET. So FinFET, if you see, so that means two sides gate will be there. Okay, double gate. So here only one gate is there, but here two side. So fin is nothing but this fin. This is nothing but fin. Fin is nothing but what channel. Here channel is available from where to where source and drain. No? So drain and source the channel is available, but here fin is available on both sides of the gate. So here this is the one channel and this is one more this side one more channel. Okay, one more channel and two gates are there between these two channels. Okay, so this is the basic structure of so you have two gates and two channels. Okay, so this is nothing but FinFET. Okay, structure of FinFET. So FinFETs are like two types are there. One is double gate and tri gate. So what is this double gate means? So double gate means what? So you have two gates over here. So you have two gates. So that is gate one and gate two, gate one and gate two with the oxide hard mask. With oxide in between this, there is the oxide layer is there. That is a oxide layer. This is nothing but double gate. Okay. Tri-gate means what? Tri-gate means you have gate one, gate two, and top gate is also there. Okay, top gate. So top gate is there, and below there is a oxide mask is there. Okay, there is a oxide mask. Okay, so this is a double gate. This is a double gate, and this is nothing but tri gate. Three gates are there, tri gate. Okay, so this is the structure of FinFET. Okay, and uh, so again you have HGFET, a short gate FinFET, and insulated gate FinFET. Okay, so this is the HGFET. Okay, this is basically HGFET, short gate FinFET, and this is the insulated gate FinFET. Okay, insulated gate FinFET. So if you see the short gate FinFET, uh, there are like so there are like 3T FinFET. 3T FinFET means so three channels are there. Here one channel, this is one channel, and here there is one more channel. Okay, and front and back gates are isolated. Okay, this see here, front and back gate are isolated, and threshold voltage cannot be controlled externally. Okay, so unless area is occupied, and insulated FET you have that means 40 FinFET, four channels will be available, and front and back gate are isolated, and threshold voltage can be controlled externally, and this is more area is occupied. Okay, so you need to remember there are two types of fins are available. One is short gate, and this one is insulated gate FinFET. Okay, and this is the top view of FinFET. Basically, this is the top view. This is single gate strip. Okay, and separate gates are there. Okay, and this is separate gate, separate two gates are there. Okay, so this is basically top view of FinFET. Okay. So fabrication, if you see fabrication, first what you are doing means lightly doped p-type substrate is fabricated, and hard mask is fabricated over the substrate. Okay, so this is lightly doped. Okay, lightly doped p-type substrate is fabricated, and over this hard mask is fabricated, and you need to etch for fin etch for channel etch for channel one channel you need to etch. Then highly anisotropic process fins are formed. See here. So you need to etch these area. Okay. So in the etch means what? That means in the fab I will tell you, like whatever the selected area is there, that you need to remove. That is nothing but etching. Okay, so whatever the selected area is there, that you need to remove. Okay, that is etching. And oxide deposition, so whatever the SiO2 layer is there, that you need to deposit on the oxide. Okay, so over the fin oxide layers are formed in the isolated of fins. And next is planarization. Planarization means you make this planarization means this surface plane. Okay, that is nothing but planarization. Okay, so how we are doing means we are doing by using chemical or mechanical polishing process. You do the planarization. Okay, and process etching. Process etching means this part is there. No, this part you need to remove. Okay, this is nothing but process etching. This part I don't want. This one I need to etch. Okay, after etching I will get this process. Get this. Okay, hard mask along with the oxide. Okay, and uh, so that means that is nothing but recess etch. By this process, we can etch the oxide. We can etch the oxide. And next, what gate oxide? Gate oxide means what? Suppose we are using thick oxide for active regions. Okay, so thick oxide for active regions. What are the active regions? Source and drain. And thin oxide for gate regions. Okay, source and drain, and thin oxide for what gate region. Okay, so again you need to develop this thin oxide for gate. Okay, to isolate the channel from the gate, to separate the channel from the gate by thermal oxidation. There is a process called oxidation, thermal oxidation. So that process we'll discuss in the fab. So gate oxide is deposited over the fins. Okay, gate oxide. So this is nothing but gate oxide. And the next is deposition of gate. So above this oxide, you need to deposit the gates. Okay, deposition of gates. Okay. So this is the fabrication of a basic FinFET. Okay. So this is the basic FinFET. So if you see the characteristics, drain current will increase with respect to VGS. Okay. Initially, ID will increase with increase of VDS. So that means the characteristics of FinFET is same as whatever the characteristics of MOSFET we already see. Okay, so I'm not going deep into this category. Why? Because you know that we already discussed the characteristics drain with respect to VDS with respect to ID. So like means initially like this is this is what linear region, and next non-linear region, and this is nothing but saturation region. Okay, so here in the saturation region, this is nowhere depending on the VDS. So where it is depending means you are depending at VGS. Okay, we already seen that means VGS one is greater than VT, VGS two is greater than VT, and VGS three is greater than VT. Okay, VT we already seen. So that different values of gate to source voltage, the drain current will increase. Okay, that is nothing but we already seen the drain characteristics. This is nothing but drain characteristics. Okay, this is same as MOSFET only. Okay, MOSFET we already discussed. Okay, so that is ID increases with increase in what VDS. ID increase in VDS after FinFET enter into what saturation region, ID becomes constant. ID becomes constant. Same as the characteristics is same as MOSFET only. Both are same. Okay, so that is operated in which region? One is that is this is cutoff region. This is nothing but cutoff region. We already seen that cases, no? So it is operated in cutoff region. Okay, and next it is operated in linear region. That means channel is acting as a uniformity is acting as a resistor. And next we already see non-linear region. Channel become non-uniform. The rate at which drain current will decrease, and channel will be pinched off, and after that channel will be moved from drain into source end, drain into source end, and that is nothing but punch through. Channel becomes constant, and ID current becomes constant. That is nothing but saturation region. That we already discussed in the MOSFET. We already discussed. Okay, same operations will be done in the FinFET. Okay, so this is the characteristics of FinFET. So what are the advantages of FinFET? Means low power consumption and operates at low voltage. Operating speed is high. Static leakage current is reduced up to 90%. Okay, and compact. Okay, this is the advantages of FinFET. Okay, and coming to the disadvantages, fabrication cost is higher than the CMOS. Controlling fin depth is difficult. Okay, controlling the fin is nothing but channel. Okay, controlling the fin depth is difficult in the FinFET. Okay, applications means you are using in microprocessor, microcontrollers, and smartphones, and like compact chip. Okay, there you are using this application. Okay, this is about the FinFET. Okay, and so next we'll see about GAAFET. Okay, these are the technologies are there in the in the VLSI. Okay, GAAFET, gate around FET. So if you see the GAAFET, yeah. So basically, like so you know that metal oxide semiconductor field effect transistor that achieved remarkable, most remarkable electronic achievement in 20th century. First commercial MOSFET they introduced around 1964. Okay, so why it is very popular? It is having high package density, small power consumption, and low cost. Okay, so this MOSFET only we are using in the CMOS, and there is a scaling factor. So Moore's law, who is the founder of Intel, he given a statement that the number of transistor count in an IC will double for every 18 to 24 months. No, so that is happening. Okay, that is happening, and so that means goes on what we call miniaturizing. Okay, or scaling down our MOSFET. Okay, scaling down our MOSFET that whatever the gate. And different parameters we are scaling down. We'll discuss about the scaling down in the next class. These are the integrated circuits when introduced around 1958. So and complementary MOSFET also, CMOS technology also, they introduced in 1967. Okay, first commercial microprocessor is introduced around by Intel. That is nothing but 4004 by using by Intel Corporation. Okay. Okay, in the year 1971. This is a 4-bit basic 4-bit microprocessor. 4-bit microprocessor. Okay. So when microprocessor subject you study, they start with the first microprocessor. This is 4004. That is invented at the during this 1971. Okay. Uh, so it is started the race of miniaturization and performance improvement. Miniaturization means what? Small size. Okay. And in ICs also you have like a dip, dual inline package, surface mount. Okay. This is nothing but surface mount package and SOG, QFF. Okay. This is like four sides you have leads. Okay. Quadruple phases we call as quadruple phases like the PLCC, VGA. These are types of ICs you have. Okay, and like I told you, no, Jordan Moore, who is the founder of Intel, so known as the Moore's law. He given 1965. He given a statement. Okay, he started the industry roadmap with potential profit, and semiconductor and industry come to a largest in CMOS technology. So, if you see the Moore's law coming to the Intel. In 19, Intel was 4004 was introduced around 1971. This is 1971. Next year they started with the 8008, 8080, 8086, okay, and 286. Okay, these are nothing but a number of yeah. So this is year 1971, and this is nothing but number of transistors in an IC. Okay, 29,000, 1,20,000, and 1985 80386 and 1989 1989 4 to 80486. It consists of what is this 1 crore 18 lakhs, no, 1 crore 18 lakhs, like that. Pentium 1993, Pentium 2, Pentium 3, Pentium 4, Pentium 4 pre-slot. Okay, so these are different transistors per count. Okay, so that means you have now in VLSI you have 100 crore transistors within an IC. 100 crore transistor within an IC. Now we are working in nanometer technology. That is that too. We are working in 3 nanometer or 2 nanometer technology. Okay, so recently TSMC company they come up with a chip with the 2 nanometer technology. Okay, this is basically my CMOS circuit. Okay, in the fab we will discuss. This is nothing but basically P substrate. In the P substrate, we can fabricate NMOS. Okay, NMOS, that is N plus and N plus, and this is body. Body is fabricated with P plus. Again, one more well is there. So one more well, that is nothing but N well. N well is nothing but N substrate. It is acting as N substrate. In N well, we fabricate P plus regions, two P plus regions, and this is nothing but my body for the PMOS. Okay. So like this, we can fabricate. This is nothing but weld technique. Okay, this is nothing but what? Weld technique. Okay, there is one disadvantage in the weld technique, that is nothing but latch up. Latch up also we'll discuss. Okay, what is this latch up? What are the disadvantages? So in order to overcome this latch up, we are going for twin tube process. This also we'll discuss. Twin tube process. Okay, twin tube process we'll discuss. Okay, this is basic CMOS process, CMOS technology, and this is a basic planar transistor. We already studied. You have source, gate, drain, and next you have like a p-type substrate. Above this, n plus regions are diffused, and this is the channel region. Okay, length of the channel. Okay, and this is depletion region, and how the channel is forming for the enhancement MOSFET, and how we can operate the depletion mode. This is enhancement. No channel is there. Okay, so already no channel is there. We need to induce. We need to internally develop the channel between source and drain. Okay, that is a planar transistor. We already studied in MOS, PMOS, all those things we already studied. Okay, and this is planar. This is a planar MOSFET. Basically, this is a channel. Okay, this is nothing but channel. Top view. Okay, this is nothing but channel between the drain and source. Okay, and this is the basic structure of planar MOSFET. We have p-type substrate and source and drain and gate. and there is the oxide layer. Above this, there is a polysilicon or metal. Okay, and so what are the drawbacks of planar transistor? Means not long ago, transistors were planar. They were large enough to degrade the problems arising from having small gate and such leakage currents are there. Okay, so like we can support up to 32 nanometer only. Okay, so we can support the planar this one CMOS up to 32 nanometer only. Okay, as manufacturer process advanced, what happens? If you are go on scaling your transistor, new issues came into the planar transistor. What are the planar new issues? There are short channel effects and variability, quantum tunneling leakage, and mobility degradation. These all are come into picture. Okay, these all problems come into picture, and so there is a need to go from this planar technology into other technology. Okay, so now FinFET came. So now FinFET, so below 32 nanometer technology, we can go for FinFET. Okay, so FinFET I told you. So this is one of the resolving this issue is nothing but three-dimensional configuration. FinFET is a three-dimensional configuration. I told you like two gates are there, two channels will be there. Okay, so with a channel gate on three sides, channel gate on three sides. Okay, and so that means they engineers they considered multi-gate devices such as FinFET, pin-shaped FET, bringing like that known as FinFET transistor. This FinFET also it will can support up to 3 nanometer only. It can support up to which nanometer? The two, sorry, 22 nanometer only it can support. Okay, again some problems will come. Okay, so these are the advantages of FinFET over planar MOSFET. Okay, these advantages already we already seen in the FinFET. Okay, and FinFET is multi-gate FET. Okay, we already seen triple gate FinFET on it. This is the bulk silicon. This is the bulk on SOI and double gate FinFET on SOI, and this all around gate is nothing but we call as this is all around gate. Okay, we call as a GAAFET. Okay, GAAFET, and independent double gate FinFET, planar double gate SOI. These are different multi-gate FETs. Okay, so this is also we are using GAAFET. Okay, the gate around all around gate FET. Okay, all around gate. So Intel showed 22 nanometer wafer. Intel developed the forum in around September 2020, 2009. Okay, so they given that size of the SRAM cell is around 22 nanometer. This is basic. Intel used 3D tri-state process. Okay, that means they use the FinFET technology only. Okay, so FinFET 3D tri-state gate process. This is 22 nanometer wafer. Okay, and what is the drawback of FinFET means? FinFET is also limited to its exhausting its two generations. Um, Suppose at 3 nanometer, when you go beyond 3 nanometer nodes or beyond, uh, FinFET no longer control the leakage current and other short channel effects. Okay, so it will no longer control this short channel effect or leakage current. Okay, and again go on shrinking. Scientists need to see the new technology on this scaling. If you scale further the transistor, they need to see the new technology. Okay. So what is the technology? New technology is GAAFET. Okay. GAAFET. So below 3 nanometer process, we need to go. There are some issues in the FinFET. Okay. So what are those? We need to go for the other technology that is nothing but GAAFET. Okay. So there is some expiration date for the FinFET. Okay. So and after last decades, there is evolution game that is nothing but gate that surrounds the three sides of channel. Okay, that is nothing but gate around FET. Okay, that gate that surrounds the three sides of the channel. That is nothing but we call as GAAFET. Okay, that is similar to cylindrical channel encircled by the tube-like gate. Okay, this is arrangement is nothing but gate all around FET. Okay, we call as GAAFET. Okay, gate all around FET and with the nanowires and nanosheets. Okay, they use nanowires and nanosheets. Okay, so here. So this design is more evolved in the build than between FinFET or planar transistor. They use nanowires and nanosheet technology are currently in progress, raising the channel, allowing the bits to scale as needed. Okay. So here this is GAAFET. Okay. So normally this will be like horizontal and channel around this. Okay. So this is nano wires. We can call it nano wires, and these are nothing but nano sheets. Okay. So gate around FET. Okay. Gate around FET. So gate will be like this. Okay. So gate around FET. Okay. So this is the channel, and in between there is a gate. Okay. This is the basic structure of GAAFET. Okay. So first GAAFET is showcased in 1988 by Toshiba, which was the vertical nanowires. Okay, they used vertical nanowires. That is nothing but GAAFET. That was surrounded by the gate transistor, surrounding gate transistor. We call as HGT. HGT is the surrounding gate transistor. Okay, first GAAFET. Okay, first GAAFET they used by the 1988 by the Toshiba company. Okay, so gate all-around field effect transistor technology is believed to be successor to FinFET. Okay, it will provide the better performance at the smaller size. Suppose if you go below 7 nanometer technology nodes also, it can support. Okay, if we are using nano wires or nano sheet structure used for fabrication of GAAFET transistor. So here it will alignment of GAAFET structure can be parallel or perpendicular to the substrate. Okay, depending on the implementation it can be parallel or perpendicular. Okay, so MBCFET using GAAFET transistor. You know the company Samsung. Samsung took first step position to itself a leader in presenting the multi-bridge channel FET. Okay, MBFET is nothing but what multi-bridge. Okay, MBFET is nothing but what multi-bridge, multi-bridge channel FET. Channel FET, CFET. Okay, MBC FET technology at its 3 nanometer manufacturing process. This technology integrates new gate all around transistor as a main innovation. Okay, main innovation. Okay, first Samsung company came up with multi-gate channel FET or MB FET at its 3 nanometer manufacturing. So here, what is the advantage means whatever the process technology when you are going for planar MOSFET or FinFET and GAAFET, that process is same only. Okay, the technology process is same only. Just you are changing the technology. Okay, that is the main advantage. You are going to different technology. Okay, suppose if process is different means you need to invest more crores of rupees or millions of rupees to set up that fabrication process. Okay, so this is the leader in Samsung foundry business. Semiconductor R&D center are holding a three finger. Three finger means what? Symbol of technology. Technology means 3 nanometers, celebrating the company of first ever product of 3 nanometer process with GAAFET architecture. Okay, they used the same technology process and they used which one? GAAFET. Okay, gate around the field effect transistor. Okay, so GAAFET. Okay, so GAAFET advantages if you see over the Samsung. So they use the nano sheets. Okay, so Samsung transistors are nano sheets. Okay, stacking in vertical with horizontal nanosheets like stacks, printer paper, replacing the traditional pins. Okay, so compared to FinFET, Samsung highlights three advantages. Okay, no need to. So what are the three advantages? No need for extra area to improve the speed. Okay, no extra area is required to improve the speed. Okay, nano sheets are stacked vertically instead of adding parallel pins. Okay, it is expected that MBFET will be able to replace FinFET without changing the size of configuration of the device footprint. Okay, it will. I told you, know, it support the same process tools and manufacturing methodology. So whatever the manufacturing methodology or process which you are using the FinFET, that they use for the same GAAFET. Okay. So if they are using same tools or same manufacturing methodology, they can reduce the cost. No, they can reduce the cost or they can accelerate the implementation. Okay, all these things they can do for a GAAFET. Okay, so this is the GAAFET. So these are the GAAFET advantages over the FinFET and MOSFET. Okay. So GAAFET higher speed is achieved with smaller transistor oversize as compared to FinFET. Okay. So we are using nano wires or nano sheets, no, to apply the GAAFET, which gives the advantage of raising the channel or channel with scalability. Okay. So we can easily transition from FinFET to GAAFET. That is, you can use same like fabrication, reduce the cost for manufacturing or quickly implementing these new technologies like this. Okay. So why we are going for this shrinking and all those things means, actually, we are using day by day what happens, technology is changing. We are going into AI, augmented reality, or we are going into what we call IoT, okay, Internet of Things, and mostly we are using handheld devices, okay, with more features, okay. So so technology is changing. Okay, so recently we are into 3G, 2G, 3G, 4G. Now we are into 5G. Okay, sometimes we will convert into 60, or Elon Musk is coming with some more technology, like without SIM we can operate the phone. Okay, day by day the technology is changing means, so based on that requirement, we need to uh, um, change the technology in the VLSI only. This VLSI as well as this embedded or this augmented reality, machine learning, and all those things are related with the VLSI. Okay, parallelly they will develop each other. Okay, so when we are lagging means that will not develop. Okay, so every time we need to develop the things. Okay, now develop we should change the technologies. We need to see the disadvantages in the FinFET, and we need to go for their GAAFET. Again, GAAFET also below 2 nanometer, you will get some issues. Okay. Now the future is during 2030. That is nothing but CFET. Okay, complementary FET. Okay. So these are the so due to these technology improvements, we are going into different technologies in this one. And I'll show you one more slide. Yeah, see here. What is the so here? This is the transistor development. First point contact transistor. Okay, first transistor is what, point contact transistor. Okay, point contact. This is the point contact transistor. Okay, so basically there is a single in the classification also we seen one is first transistor is point contact transistor, single junction transistor. It consists of only one junction, two metal contacts. Okay, and there is a reverse side. There is a germanium in there. Okay, I told you before 1947 or like that, they used germanium in the transistor, but after that they realized that germanium is not constant with the temperature, and it is having less energy gap, and also the electron is there in the fourth orbit, that is unstable. Okay, with the temperature, it can withstand up to 100 degrees Celsius only. After that, scientists realized that we can use silicon. Silicon is the best material, and what we call there are simple techniques are used to make the pure silicon. Okay, so that's why they switch into silicon. Silicon, it can stand up to 150 degrees Celsius temperature also. It is stable. Okay, and so that is indirect band gap. I told you indirect band gap. Silicon is indirect band gap, and indirect silicon and germanium. And direct band gap means we are using for like LEDs and LEDs and lasers, like gallium arsenide we are using for direct band gap. Okay, this is point contact transistor. Okay, this is the point contact transistor. And bipolar junction we already seen, metal oxide we already seen. Okay, this is FinFET. Okay, so see here, planar FET, FinFET, GAAFET. GAAFET means what? Nanowires. You have nanowires. Okay, as a channel, nanowires. And MBC FET, nano sheets. MBC FET is nothing but nano sheets. I told you, no, Samsung came up with the MBC FET. Okay, MBC FET. Okay, planar and FinFET limitations, nano sheet advantages. Okay, so the future is after This one, there is CFET. Okay. Hello. Somebody unmuted. Just mute yourself. If you have any doubts, you can ask after completing my lecture. Who is hello? Yes. Yeah. So this is complementary CFET. CFET. Okay. The feature is CFET. Okay. The stack both NFET and PFET via each other. Okay. There is a NFET and CFET, PFET via both each other. Folding up NFET and PFET eliminate the N2P separation of low bottleneck. Okay. So there is a IMAC Technology Forum in San Francisco. IMAC CEO laid out 20 years roadmap for the evolution of semiconductor technology. Okay, 20. There is a 20 years roadmap in the semiconductor technology. Normally, 2018, we are using what FinFET. Okay, this is a metal pitch, and 2020 also we are using FinFET, and 2022 we are using FinFET. 2024 we introduced the GAAFET. Okay, so we are into GAAFET and nano sheets. Okay, 2026 also we use the GAAFET and metal pitch is 18 that is 18 nanometers, and 2028 also we use GAAFET. 2030 also we use GAAFET. Okay, so what happens there is a continuous dimension scaling is there. So there is a continuous dimension scaling as Moore's law told that the number of transistors will count will will double for every 2 years. So what happens we can't make the transistor size to the size of the atom, no. So we can't change. We need to go for other technologies to or it will becomes constant or it will satisfy the most law. We don't know, but the future is what a CFET. Okay, future is what complementary FET. Future is complementary FET. So that means again in 2032 we use the CFET. Okay, device and material innovation, and so metal feature 16 to 12, and it will be constant only. And metal tracks are less than 4 CFET 2034, and 2036 we use CFET atomic. Okay, metal track is less than 4, and metal pitch is 16 to 12 nanometers. Okay, so this is the potential roadmap of our basic whatever the devices we are using in the VLSI. Okay, hope you understood this section.